Hello, everyone, and welcome to our second lecture in our exploration webinar series. My name is Christine Kennedy, and on behalf of the Office of Alumni Engagement, I'd like to thank you for joining us for our webinar, Painted Black, the Solar Eclipse of 2024. Ooh, ah. Before I begin, I'd like to acknowledge the land on which this webinar is taking place. I'm in my house, which is in Ancaster, just up the street from McMaster, and Laura is in Hamilton, and all of the lands on which we reside are located on the traditional territories of the Mississauga and Haudenosaunee nations and within the lands protected by the Dish with One Spoon Wampum Agreement. Tonight, I am so excited to introduce our speaker, Dr. Laura Parker. Now, if you need to leave the talk, don't worry, because you will be getting a link to a recording in about an hour after the talk. So around 9 p.m., you'll get a link to this. So if you need to leave for whatever reason, but you're really excited because you don't want to miss any of the information, fear not, you will get it later today. If you have a question, so Dr. Parker's presentation will be about 30 minutes or so, and then we have lots of time for Q&A. So if you'd like to ask a question, feel free to put that in the little box, include your question in the box below the video. And I'd like to thank everyone who pre-submitted their questions. We had lots of great questions, and Dr. Parker has weaved those into her presentation. For those of you who are familiar with anything that we do with astronomy, Dr. Parker is one of our regulars. She is a professor and university scholar in the Department of Physics and Astronomy. She did a fantastic talk, I think last summer. We did Hubble and the
JWST.
Yeah, I was trying to get all the acronyms. Yes, thank you. She is an observational astronomer, and her research group is interested in questions related to galaxy evolution and observational cosmology. I had the pleasure of meeting Dr. Parker when she was my professor in the pandemic. I took her second year of sort of astronomy for dummies called Big Ideas. Fantastic course. And now anytime I want to do a talk on astronomy, I go right to Dr. Parker because she is so amazing and she really speaks at a level that we can all enjoy. So thank you, Laura, for joining us. Take it away.
Thank you so much, Christine. So I'm very happy to be here this evening to talk about an extremely exciting upcoming event that if you are like Christine and I and you're local to the Hamilton area, you're going to be particularly lucky because we are on April 8th, 2024, going to experience totality, which is a total solar eclipse. And so today what I want to do is explain a little bit about what eclipses are, when and where can you view this particular one coming up in April? And in particular, I want to focus a little bit on safety. So how can you safely view a solar eclipse? And then I'm going to end tonight's presentation before the Q&A talking a little bit about eclipse science. So first, let's talk a little bit about eclipses. And it's important to differentiate the two different kinds of eclipses. And in a minute, I'll show you some images which will help explain the way these two different kinds of eclipses work. But basically, you can think about lunar eclipses being eclipses of the moon. So that's when the moon's light is blocked from our view. And solar eclipses are when the sun is blocked. And so the sun's light is blocked from our view. And the purpose of this slide is to give you some idea for how common these occurrences are of eclipses. So for lunar eclipses, if we just focus on the bottom line, which says total, the last lunar eclipse seen from my location here in Hamilton was in 2022, so just about a year ago. And then the next one, total lunar eclipse, where the moon is completely blocked, happens in March 2025. So that's only a couple of years apart, and that's kind of typical. The moon is blocked more often than the sun, so lunar eclipses are more common than solar eclipses. And if you're lucky and you have good weather, which of course we don't always here, but when you do, you can expect in your lifetime to experience a bunch of these. So they're always amazing. If you like to do photography, they're a wonderful thing to take pictures of to see a lunar eclipse progress, but they're not so rare. It's something you can expect to experience lots of times in your life. Solar eclipses, on the other hand, and particularly total solar eclipses, like we're going to talk about tonight, are not nearly as frequent. So the last total solar eclipse we experienced in Hamilton was in 1925, and we will experience one this coming up very soon in April. And then if you want to see another one and you don't want to move around the globe to find it, you have to wait for more than a century. So the next total solar eclipse is not until 2144. So this just gives you some sense of lunar eclipses happen pretty regularly. Solar eclipses are pretty special events, which is why we're so excited about this one coming up in April. But let me first explain a little bit about the two different kinds of eclipses. So in both cases, both lunar and solar eclipses, we're talking about the sun, Earth, and moon system. And it's a question of which thing is in which order. So the lunar eclipses happen when light from the sun, which normally would bounce off the moon, allowing us to see the moon, the light from the sun is blocked because the Earth is in the way. Or another way of saying it is a lunar eclipse happens when the Earth's shadow falls onto the moon. And so this happens not so infrequently. And when the moon is totally blocked, when it's in this dark part of the shadow, that's called a total lunar eclipse. And when the moon's light is only partially blocked from our view, when it's in this lighter part, that's called a partial lunar eclipse. So when the moon is in this penumbra, as it's labeled on this diagram. But I think what's nicer to see rather than this diagram is to actually view one of these things happen. So here is a time lapse of a lunar eclipse, and we'll watch it a couple times, but I'll explain what you're seeing here. So first thing that happens is you see the shadow of the Earth come across the moon, and then you reach the period of total lunar eclipse, and the moon is fainter, but you can still see it, but it looks pretty red. And then the shadow moves across the sun, moves across the moon, and now you're back to seeing the complete moon again. So let's just watch it one more time. The shadow of the Earth falls across the moon. You're at the total lunar eclipse. The moon looks red, and then the shadow moves across, and you're back to seeing the moon as usual. So these lunar eclipses clearly happen when there's a full moon. And what's really remarkable is, although the moon is really faint, you can still see it during the total lunar eclipse, but it looks really red. So why? Why does the moon look red during a lunar eclipse? So if we go back to this diagram where a lunar eclipse happens when sunlight is blocked by the Earth and a shadow is cast on the moon, and so you don't see the moon. So why are we seeing the moon and why does it look red? And the answer is actually related to the same reason why we have red sunrises and sunsets. So it turns out that light from the sun scatters through the Earth's atmosphere, but light from the sun comes in all colors of the rainbow, and it's the blue light which is preferentially scattered. And so when we're looking at sunrise and sunset, we're looking towards the horizon, we're looking through a ton of the Earth's atmosphere towards the horizon, and the only light that makes it to our eyes is the red light that can travel through the atmosphere without being scattered. A similar thing happens during a lunar eclipse. So the shadow is cast on the moon, but some light from the sun, a lot of the light gets blocked by the Earth, but some can pass through the atmosphere and illuminate the moon. Not much, so the moon is very faint, and the only light that can pass through the atmosphere is that red light that is not scattered. So sunlight shines through the atmosphere, most of it gets scattered away. The red light can make it to the moon, bounce off the moon, and enter our eyes, and the moon will look red and faint to us. So those are lunar eclipses. Amazing, beautiful. You may have experienced some in your life already. You can anticipate experiencing them again, but it's the solar eclipses that we want to focus on tonight. And again, it's the sun, moon, and Earth system, but now we've changed the geometry a bit. Instead of the Earth casting a shadow onto the moon is now in the way, blocking the sunlight and casting a shadow onto the Earth. And so if you look at this picture, the shadow of the moon is covering a pretty small area, particularly this darkest part, which is where you would get a total solar eclipse, is casting a pretty small shadow onto the surface of the Earth. And so the area of the Earth, which experiences a total solar eclipse when these things happen, is pretty small. Whereas during a total lunar eclipse, the whole nighttime of the Earth can see the eclipse. Whereas a solar eclipse is one little part on the Earth that can see it at a given time. So let's see this one on April 8th, 2024. This is the model of where we expect the shadow of the Earth to be cast. So this will play a couple of times, but you see this big fuzzy region. That is the part on the Earth which will get a partial solar eclipse. So a little bit of shadow, but the sun will not be completely blocked. And then there's this dark black spot, which is moving across North America here. That is the path of totality, where the moon will completely block out the sun, and the sun for a brief period of time, which we're going to talk about, is going to be not visible to us. And if you look carefully, you can see right about now that dot moves over where I'm sitting today in Hamilton. But it's not only Hamilton that's going to experience this total solar eclipse. It's this entire area covered by this little black dot. So from Mexico here, across parts of the United States, into southern Ontario, skimming near Montreal, and then out over Atlantic Canada. And so there's quite a big part of Eastern Canada that's going to be able to experience this total solar eclipse. And just to give you a view of another one, so this is not the 2024 eclipse, which hasn't happened yet. This is real satellite imagery from an eclipse in 2020. So you're seeing the satellite image, and there you can see that black shadow, that spot. That is the total solar eclipse of 2020 passing over part of the Pacific and part of South America as seen by the satellite imagery. So it really is this dark spot moving across the surface, which is this shadow of the moon moving across the Earth, blocking the sunlight. So let's talk a little bit more about the April 8th, 2024 eclipse. This is the path of totality, where the darkest pink is where 100% of the sun will be blocked. And then as you go to the lighter colors, it's less and less complete in terms of how much light will be blocked. So if you're along this nice path, so if you're in Niagara or Hamilton or near Montreal or near Fredericton or Summerside, you're going to be excited because you're along this path of totality. Everybody else is still going to have a partial. Most of all of North America will have a partial solar eclipse, but only along this one path will the sun be completely blocked, and where it will appear much more like nighttime in the daytime, which I'm going to talk a little bit more about. I should just zoom in a little bit more for people who are local here. This is one of those things where there's some bragging rights. Hamiltonians love to argue with Torontonians. So this is one case where Hamilton wins out. So Toronto will be in the path of a partial solar eclipse, almost complete, but not complete. Whereas here in Hamilton and down towards Lake Erie and over towards Niagara, we will be in the path of totality, where the sun will be completely blocked. But let's talk about that eclipse a little bit and this period of totality. So the eclipse on Monday, April 8th, 2024 will start at about 2 in the afternoon. So just before kids get out of school. I believe this is the last week of classes at McMaster in April, and the eclipse will go until about 4:30. So from when the shadow first starts to move across the sun until the shadow leaves the sun, the entire process is about 2.5 hours. But the part that we're all most excited about, this time when the sunlight is completely blocked, is 1 minute and 50 seconds. So depending on where you are in that path of totality, it might be a tiny bit longer or a tiny bit shorter, but this is for Hamilton, it's 1 minute and 50 seconds. So this is the only time ever in your life when it's safe to stare at not the sun, but where the sun is in the sky. So I'm going to talk more about safety in a second, but during totality, you can actually look in the direction of the sun without any safety equipment at all, but only for that 1 minute and 50 seconds. And the other thing I wanted to point out in this image, you can see just at the very, very beginning of the eclipse and at the very, very end of the eclipse, there are these bright little spots. Those are called Bailey's beads, and I think it's a really cool phenomenon. So you have the moon that's basically blocking out the light from the sun, but the moon has topology. It has mountains, it has craters, the surface is uneven. And so right at the moment that the moon, the shadow is moving on and off the sun, you will have little rays of light that can just make it through some of those craters, some of those irregularities in the surface of the moon. And so you'll get these bright spots at the very beginning and at the very end of the eclipse. And then for 1 minute and 50 seconds, it will be completely blocked. Now I'll just leave this up for a second, but I realize that this webinar, and there's lots of alumni from McMaster and folks who are online who may not be in Hamilton, and you may be wondering, am I in the path of totality, or how much of the eclipse am I going to be able to see? And that graphic I showed you a few minutes ago with the dark pink line, that comes from this wonderful website, Time and Date. The website is there, and there's a QR code that takes you there as well if you want to snap a quick picture. This website allows you to click just to pin any location on the map, and it will tell you what you can expect for the April 8th, 2024 eclipse. It's a really handy resource to have handy. Okay, time to talk about safety a little bit. So of course, you should never look at the sun. You should never look directly at the sun. The only time you can look at this is during the period of totality. And then of course, you're not looking at the sun. You're looking at the moon blocking the sun. During the rest of that period of the eclipse, when the sun is only being partially blocked, it is absolutely unsafe to look at the sun without eye protection. And by eye protection, I do not mean sunglasses. I mean solar viewing glasses, a solar filter of some kind. Now, of course, adults should know, never look at the sun, but we're going to hopefully be enjoying this experience with lots of people in our lives, perhaps lots of community members. Pay attention that nobody is staring at the sun. There's lots of horror stories during total eclipses where people do damage without realizing it. So please don't look at the sun. If you would like to have a safe way to do this, the best thing I would recommend is to look at buying yourself an inexpensive pair of eclipse viewing glasses. Again, not sunglasses. And I've included here a couple of links to ones that are for sure safe for looking at the sun. But also I wanted to point out some really exciting news, which is for anyone who happens to live in the Hamilton area, we're really fortunate that McMaster has, and our provost at the university, has decided to buy a pair of safe solar viewing glasses for every single resident of Hamilton. So more than 500,000 pairs of sun viewing glasses have been purchased and are starting to arrive. And so stay tuned for some information about the distribution of those if you live in this area. For people who are further afield, I encourage you to perhaps look at buying your own pair of solar viewing glasses. They're not expensive. They're folding paper. They look like 3D glasses at the movie theater, but they have a filter that makes it safe to look at the sun. But if you don't have safe solar viewing glasses, there are other ways you can experience the eclipse safely. So one of them, and maybe the simplest one, is to do pinhole projection. And so the idea here is you take a piece of paper, put a little pinprick hole in it, and then let the sunlight pass through that. And you project that onto a screen, onto a white wall, onto another piece of white paper. And the image doesn't show super clearly here, but this is during a partial solar eclipse, and you can see the crescent shadow across the surface of the sun. So you can do simple pinhole projection with just a piece of paper. If you want to be a little bit more elaborate, you can build yourself a pinhole eclipse viewing apparatus like this one. Take a cardboard box, put a little hole, ideally cut a little window and put a piece of tinfoil and cut a hole, or even just a pinprick hole works. Project that into the far side of inside the cardboard box, put a white piece of paper, and then you can put your head through the bottom to look at this if it's a big box, or build a little window over here to look in the box. But you can build yourself a very simple pinhole projection device that allows you to safely watch the eclipse progress if you don't have solar viewing glasses. If you want to have a large number of pinholes all at once, then you can simply use a colander. So this is a classic experiment you can do by taking out a colander and again, directing the sunlight through the colander, projecting it onto a screen or onto a piece of paper. You will see many replicas of the partial eclipse as it progresses, and you can see it progress. And let's imagine you do no preparation at all. You have no apparatus whatsoever, no safety viewing glasses. Sometimes nature will provide one for you. And so there's lots of examples from previous total solar eclipses of people taking pictures of the shadow of leaves on the ground and realizing that there's tons of partial solar eclipses that you're able to see. And that is the light filtering through holes in the leaves, creating this beautiful pattern. So it's like nature's pinholes. And in addition to a pinhole camera, you could also have a friend with a mirror, and you can direct the sunlight from the mirror onto a screen or onto a piece of paper. So here's an example of using a mirror or maybe even a CD to reflect this onto a piece of paper. And I should highlight, this is my colleague, Dr. Rob Cockcroft, who's doing a lot of the work at McMaster getting ready for this total solar eclipse in April. He had a wonderful experience back in 2017. He traveled to the US to visit to a place which was going to experience a total solar eclipse. And so these past photographs with all the pinhole examples are things that he did during the 2017 total solar eclipse. And then you have totality. So you do all this pinhole viewing and looking at the eclipse progress, but you'll have this brief period, for us 1 minute and 50 seconds here in Hamilton, where the sun's completely blocked. And then you can take off your solar viewing glasses, you can not worry about the pinhole, and you can actually look with your eyes at the total solar eclipse. But don't look for too long, because it won't take long till it's all over and you'll start to see the sun peeking around the moon again, and back to needing to use that safety equipment to watch the sun. Okay, so why are these solar eclipses so infrequent? So why don't we experience them all the time? And you might naively expect that we should. So if we picture a little graphic here of our little part of the solar system, imagine we have the sun off to the right, and there's sunlight shining towards the Earth. And then the moon is in orbit around the Earth. So the little dashed line, that's the moon moving around the Earth. And the side of the moon that's facing the sun here is always illuminated. So it's white, and the side away from the sun is always dark. But our view on Earth, when we look up at the moon, if the moon is in this part of its orbit, then anyone on the Earth is going to see the dark side of the moon here, this shadow side. So we're going to see a new moon. And if you wait 2 weeks, because the orbit of the moon takes a month, if you wait 2 weeks on the other side of the orbit, if you're here on Earth and you're looking up at the moon, you're going to see the moon fully illuminated by the sun. So you're going to see the full moon. So once a month, you see a new moon, and then you see first quarter, and then you see a full moon, and then you see a last quarter, and then the cycle repeats every month. So if you just look at this picture, you might think, well, the sun is shining in this direction. Why do I not get an eclipse every single month? So when the sun is on this side, the moon casts a shadow on the Earth. Why don't I get a solar eclipse every time that there's a new moon? And on the other side, why don't I get a lunar eclipse with the Earth casting a shadow on the moon every full moon? So if everything were perfectly lined up, you might expect there to be eclipses all the time. When I look at this simple diagram, it looks like I should have an eclipse every time the Earth, the moon, and the sun line up. But things are not quite that simple. And so in our solar system, the main reason why we're not getting eclipses all the time is because the plane of the orbit of the Earth around the sun is not the same as the plane of the orbit of the moon around the Earth. So it is true that solar eclipses happen during new moon and lunar eclipses happen during full moon, but they don't happen every month, because it only can happen when the orbit of the moon around the Earth crosses the orbit of the Earth around the sun. So things have to be perfectly lined up. And because the orbits are tilted relative to each other, it doesn't happen that often that they line up perfectly. So that's the reason why lunar and solar eclipses are not happening all the time. And it's just because of these tilts in the orbit. And there's an extra effect too, which is interesting, which is that not only are the orbits tilted, but they're also not perfectly circular. So the orbit of the Earth around the sun is not a circle, it's an ellipse. And the orbit of the moon around the Earth is an ellipse, it's not a circle. And the effect of that is that depending on where the moon and the sun are in their orbits, we can see those objects being a slightly different size in the night sky. So let's think about the moon for a second. So when the moon is in its elliptical orbit around the Earth, when it's at the furthest distance from the Earth, the moon's going to look a little smaller to us than when the moon is at its closest distance to us, as it is in this elliptical orbit. And in terms of eclipses, why this is really interesting is sometimes you could have the geometry perfect, we have these tilted orbits, but everything's lined up perfectly, and you would expect there to be a total solar eclipse. But if the moon is at its furthest point from the Earth in its orbit, it may not be big enough to totally block the light from the sun. And so when that happens, you don't get a total solar eclipse. I'll show you what you get in just a second. And one other thing I wanted to note is that because of tidal interactions, the moon is actually slowly over time drifting away from the Earth. And so the moon over time is getting a bit further away from us, which means it's looking a little smaller on the night sky. And in about 600 million years, there will be no more total solar eclipses. I mean, that's a long time, so we don't have to worry, but it's interesting to think that in 600 million years, half a billion years from now, there will no longer be total solar eclipses for whoever happens to be on Earth at that time. It's also kind of just serendipitous that on the sky, the moon and the sun, despite them being physically very different size objects, the sun is way bigger than the moon. They just happen, from our perspective, to look like the same size on the sky. It didn't have to be like that. It's just a coincidence. So in terms of solar eclipses, you can have the total solar eclipse like we're going to have in April. You can have a partial solar eclipse where only part of the sun is blocked. And then you can have these special ones where the moon is a little bit further away in its orbit. And so it's a little bit smaller and it can't totally block the sunlight. And that kind of eclipse has a special name. It's called an annular eclipse because it leaves an annulus, a ring of light from the sun. The moon doesn't totally block the sun. And those annular eclipses happen with about the same frequency as total solar eclipses. And there was actually one earlier this year that could be seen from parts of the US. You could have seen a partial eclipse, possibly from parts of Canada, but like usual, the weather was terrible. So people didn't get to take nice pictures. And I just wanted to highlight where eclipses are for the period from starting a couple years ago and going forward for the next 15 years or so. These are the locations of where you'll be able to see a total solar eclipse in blue or a total or an annular, one of these beautiful ring eclipses in red. And you can see the curve for April 8th, 2024, passing through Hamilton here. But if you're not in this area, or if we have terrible weather and you're really, really anxious to experience one of these eclipses, this is where you'd have to plan your travel. And what I would recommend is maybe looking at Australia. It seems like they're going to be the lucky ones for the next little while, with a couple of total solar eclipses coming up over the next 15 to 20 years. Okay. So let's imagine you're fortunate, you get to experience a total solar eclipse. What is it like? What happens during an eclipse? Why do people get so excited? So one, I think the fact that the sun gets totally blocked and you get to experience a brief moment of nighttime in the daytime is kind of unnerving and not something that's familiar to people. And so for that reason, it's really amazing. But there's also some cool things that happen. So there's been a lot of observations over the years about strange animal behavior during total solar eclipses. So nocturnal animals like bats can come out. Birds can change their behavior. There's less bird song. Animals really think it's nighttime, and so they behave differently than they normally would in the day. You can experience a drop in temperature anywhere up to about 5 degrees Celsius, typically a couple of degrees. It will get cooler. The winds will change both before and after the eclipse. During totality, if you look really carefully, you can actually see stars and planets in the daytime, which is normally the sun is way too bright to see faint things like stars and planets in the daytime. Also, as the eclipse progresses and you start to have more and more of the sun blocked, so eventually you have a sliver of the sun blocked right before totality, as the amount of sun that is visible gets smaller and smaller, shadows get crisper and crisper. And so fuzzy shadows become much crisper. You might even be able to see individual hairs from your head as shadows on the ground. So that's a cool thing to try to observe during the eclipse. And I also want to highlight that, the weather might not agree with us. It's April in Canada. Often the weather's not great. What would you experience if it's unfortunately not a great day weather-wise? And certainly you'd experience still darkness. So here's a nice time series a series of photos from a previous total solar eclipse on a day that was relatively cloudy where this particular observer was. And what you can see is it gets much darker. And a lot of these things I've talked about, the winds changing, the temperature changing, strange animal behavior, all of that stuff will still happen. You just won't get to see the sun blocked on the sky, but you still will get to experience the darkness in the daytime and some of the strange things that happen during a total solar eclipse. So I wanted to end tonight, before taking your questions, with a little bit about the science of eclipses. So a lot of people get really excited about total solar eclipses if they study the sun, if they're interested in the sun or in stars. And the primary reason for that is when you have a total solar eclipse, you're blocking the main light from the sun, which is incredibly bright, which is why you can't stare at the sun because you'll damage your eyes. But the part of the sun that we're blocking is not all that there is. There is an outer atmosphere around the sun called the corona. And there's really interesting physics that happens in the corona. And usually it's too faint to see because the main part of the sun is so bright, you can't see the corona. During an eclipse, you can. And so lots of solar scientists take data during total solar eclipses to study the properties of this corona. And this is not just to understand the sun, but also what you see in the corona is material that also gets spread out into the solar system as the solar wind. And that solar wind can influence us here on Earth and impact things on Earth. And so it's important for us to understand the solar wind, and total solar eclipses give us a new window on that. Also, people who study Earth's atmosphere, it's very strange to suddenly turn off our energy source, that suddenly there's no sunlight in the daytime. And you can get reactions of the atmosphere in terms of temperature and pressure that are quite interesting to atmospheric scientists. And so if you're interested in studying the Earth's atmosphere under uncommon conditions, this is a unique viewing angle. So people who study atmospheres, people who study stars, in particular the sun, get really excited about total solar eclipses. But as you heard from the introduction from Christine earlier tonight, my area of research is actually on much bigger scales. So I study galaxies and scales even bigger than galaxies. And why I love solar eclipses is really because of the incredibly important role that one particular eclipse played in the history of modern science. And so I want to end tonight by telling you a little bit about this story. So back in 1915, Albert Einstein published his theory of general relativity. And this was a new way of explaining a really important part of nature. So for centuries, our description of gravity was that of Isaac Newton, that gravity is a force between things that have mass. So imagine you have a star and you have a planet, and the reason why the planet orbits around the star is because of gravity. They feel each other because they have mass, and how much gravitational attraction there is depends on how massive they are and how far apart they are from each other. Einstein came along in 1915 and he said, I'm not going to describe gravity like a force. I think gravity is a manifestation of the fact that masses distort space-time. And I apologize, I won't be able to give full justice to this tonight, but the idea here is that imagine you have a grid like you see on the right here. Every location in the universe, like me sitting in this room, I have a position and I have a time, this instant. So I can locate any position, anything in the universe in terms of where it is and at what time you're marking it. And so I can imagine a regular grid of all the positions and all the time in the universe. And what Einstein said is when you have something very massive, like in this example, it's the sun, something with mass distorts the space-time grid. And what that really means is it plays with the distances between objects. It also can play with time, which is fun as well. But for our purposes tonight, what's really important is that under our classical understanding from Isaac Newton of gravity, gravity is a force between masses. What that means is something that has no mass, like light. Light has no mass. Light should not feel gravity. Whereas Einstein's description from general relativity says masses curve space-time. Anything moving through that curved space-time should be influenced, whether that has mass or not. So the big difference between Newton and Einstein is that light feels gravity under the description of Einstein. Light does not feel gravity under the description of Newton. And so if you can come up with a cool way to test that, does light feel gravity or not? You'd be able to figure out if Einstein was right. So he published this in 1915, and it was realized, actually, I'll go back for a second to this picture. So imagine you have the sun here, and it's bending, distorting the space-time, and you have the Earth, and we're looking at some distant star that I'm labeling A here. So the light from this star travels out through the universe, and it just happens that from our perspective, this light passes really close to the sun along our line of sight. And so the light, because it's going really close to a massive object, which has distorted the space-time, the light will follow a curved path because the space-time is curved. And so the light gets bent around the mass. And so when we look up at the night sky and we see where's that light coming from, we think the light's coming from this location B. It actually came from A, and the light was bent around the sun. So this is what Einstein predicts should happen. Light from distant objects should be bent around masses. Newton would not predict this. And so this gives you something that is testable. Now, the problem is, how do I see starlight being bent around the sun when if I'm looking at something really close to the sun, I can't see it because the sun is really, really bright. And so the only way to measure this light from background objects being bent around the sun is to do it during a total solar eclipse. So in order to measure this effect, the light has to pass really close to the sun where the space-time curvature is enough to make the light bend. So it's only visible during a total solar eclipse when the light from the sun is blocked and you can actually see stars. And just to show you a picture, and I apologize, this does not come out well on the screen. This is an amateur astronomer's photo taken during a total solar eclipse, and there are some stars and planets that are labeled here. So during a total solar eclipse, it's briefly nighttime during the day, and you can see stars and planets. And so Einstein published this in 1916, and it was realized that this could be a real test. Can we see light from stars being bent around the sun, around a massive object? That would confirm general relativity. So again, let me just talk a little bit about the method here, and then I'll talk about the results. So let's imagine a regular day or a regular nighttime. It's nighttime on Earth, so I'm looking up at the night sky and I see the position of some star. If sometime later in the year, this star's not up at nighttime, now it's up during the daytime, that star, imagine the light from that star passes really close to the sun. It should be bent by the sun. Unfortunately, I can't see it during the daytime because the sun is really bright, unless I'm doing it during a total solar eclipse. So again, the idea is I know where that star should be because I can observe it at some other time of year when it's up at the nighttime. And now I can observe it in the daytime and see if during the daytime, the light from this star is bent around the sun. And it ends up that I can see this only because of the total solar eclipse. And again, I would think the star is over here. It's actually over here. And I know where it actually is because I've already done observations at some previous time when the light did not pass near the sun at all. So this was the test that was imagined very soon after Einstein published his theory. And then there was a total solar eclipse coming up over parts of Brazil and some islands off the coast of Africa. And so expeditions were organized to go to these two locations to take some data, observe stars during the total solar eclipse, and see whether their positions changed. And remarkably, what was measured was exactly what Einstein's theory predicted. Light feels gravity. The light follows a curved path around these massive objects. So this is an image from the original paper published in 2020. And this is Sir Arthur Eddington, who led this expedition. So the idea here was, let's go find some stars. They're marked with these black lines. So this is from the real published paper. Measure their positions, compare those positions to where they are when the light doesn't pass near the sun. So some other time of year when the light just comes straight to us from these stars. And if they've shifted, how much have they shifted? And they measured that shift, and it was exactly what you would expect from the theory of general relativity. And this was revolutionary. So this was published in 1920, but the results were actually shared a little bit earlier. So in 1919, this is an announcement in the Times of London saying, revolution in science, new theory of the universe, Newtonian ideas are overturned. So this was a unique experiment that could only be done during a total solar eclipse when you can actually see stars in the daytime, find stars that just happen to be on the sky really close behind the sun, and see that their light is deflected. So this was 1919, published in 1920, and this showed that light is bent by gravity. But this is not the only time this method has been used. It has become a ubiquitous tool in studying the distant universe. So this is a beautiful image, one of the first released images from the JWST when they released their first data last year. And what you are seeing in this image is a couple of really bright stars, these spiky objects. But the main target of these observations is there's what's called a cluster of galaxies. So galaxy is a big collection of gas and stars and dust. Each one has about 100 billion stars. So every point of light you're seeing here is an enormous galaxy. But there's a collection of them here towards the middle, the whitish, yellowish light. Those are all galaxies that live together, that are orbiting around each other. They're called a cluster of galaxies. These are the most massive things in the whole universe, these clusters of galaxies. It's because they have a lot of mass. if there's any light coming from objects behind them, that light is really going to be bent as it passes by this incredibly massive object, which has distorted the space-time a whole lot. And so if you can see all of these funny stretched out arcs in this image, that's light from background galaxies behind the cluster that's being really distorted by the mass, by the space-time curvature of this cluster of galaxies. So a prediction from general relativity, first confirmed way back in 1919, 1920 during a total solar eclipse, and now one of the primary tools we use for understanding mass and gravity of objects in the universe. So to summarize what we've talked about tonight, we have an exciting upcoming date with a total solar eclipse on April 8th, 2024. If you happen to be in the Hamilton area or somewhere else along that path, lucky to be in the path of totality, what I would recommend to you is that you take the afternoon off. Don't travel. I don't think the highways are going to be great. They're not great on the best of days, but everyone's going to be trying to get somewhere that has this path of totality. At least I think so. Take some photos. If you have a camera, you can certainly take photos during totality. Outside of totality, you need to have a solar filter in front of your camera. Do not look at the sun except for during the period of totality. Also, I recommend you try to, within that 1 minute and 50 seconds, take some time to just relax and experience it. I have not had the fortune to experience a total solar eclipse, but everyone I've spoken to who has says it's really a moving experience, and you should take the time to also just enjoy that. Stay tuned for announcements about more upcoming events organized by McMaster. So there will be lots of activities related to the eclipse, and most of all, hope for clear skies on April 8th, 2024. So I'll stop there, and I'm really happy to take any questions.
Thank you so much, Laura. I was thinking the same thing about clear skies, because for those of you who are not in the Hamilton area, it is miserable. It's miserable here. And it started to get, well, around 2 or 3, I think it was okay. It was cloudy, but this evening, while this is taking place, yeah, totally miserable. So we do not want that in April. I do want to point out that Claire has mentioned in the comments, well, you mentioned, Laura, that Hamilton McMaster has purchased, 500,000, 500,000 viewing glasses for the populace. That if you are not out in Hamilton, if you're outside of Hamilton, but you are in the path of totality, that RASC, which is the Royal Astronomical Society of Canada, they have eclipse glasses for sale.
Oh, super. That's great to know.
Yes. So if you're in Hamilton, we can get you some information, as Laura pointed out, as it's forthcoming, rolling out. But if you are in the States, or if you are in Niagara, or I think you said Eastern Ontario, Ottawa, Kingston's good.
Kingston, Montreal, Fredericton, Summerside, and then over parts of Newfoundland.
So there you go. So you can get in touch with the local RASC. So Rick wanted to know, what is a hybrid eclipse?
So I had it on my slides and then I removed it for efficiency. So a hybrid eclipse is when, depending on where you are on the Earth, you can be, during a total solar eclipse, you can move kind of between being annular and total. So they're extremely rare. So total solar eclipses, annular solar eclipses happen much more frequently, but every once in a while you can have one that kind of flip-flops between the two when you're just at this critical point, but they are very rare.
Even rare, okay. Also, now Rick has, so people are commenting in the comments here, that someone is going to be in New Mexico in April, and they really like to, so they will likely drive over into Texas for a couple days to see the eclipse. Is there a website you can recommend for finding optimal chances of clear skies based on meteorological probability? And then Dan said there's something called theskylive.com. Do you know about that? Would you recommend?
I don't know that website, no. So for short term, there's a great website, Clear Skies. I'm not going to get the URL correct, but there's a clear sky predictor, which is what a lot of astronomers will use for, is it going to be clear tonight or tomorrow night if I want to go, for example, go do some sky viewing. But for longer term kind of averages of what I should expect, I do not know off the top of my head what the best resource is for that.
Okay, well, maybe we can look that up and put it in the resources under the when we're sending out the video link. Sorry, you can purchase Eclipse. Okay, so thank you, Claire, and I will post that in the resources too for people who maybe aren't seeing the comments. Okay, so Dan is asking, when in time of years, centuries, were scientists first able to calculate or predict an eclipse, solar or lunar?
Oh, I should have done my homework more to prepare for these good questions. I mean, certainly people have experienced and viewed eclipses for as long as there's been humanity, and there's evidence of people in petroglyphs in different cultures around the world of people who have memorialized the eclipses that they viewed. When we were first able to predict it, I know that the Greeks did. I can't give you an exact date, but there are, going back to at least the Greeks, there have been predictions of when we should have eclipses. Not always perfectly accurate, but it's a long time that we've been making predictions.
Leave it to the Greeks. And another question that Dan's asking, how dark will the area be in total eclipse? Just a full night or some ambient light?
Yeah, so for us, we're kind of on the edge of totality. The sun will be totally blocked. The corona will not be totally blocked. So it's not like the middle of the night. It will be way darker, but it will not be pitch black. It'll be like darker than twilight, but not as dark as the middle of the night.
Okay. And so I know when I was doing a little bit of research for coming up with the synopsis, when we worked on the synopsis together, that the path of totality, when I was looking at the map, and you just said we're kind of on the edge. And so we have 1 minute and 50 seconds, and we're on the edge. So where around us is sort of the biggest totality, and how long would that be?
So the maximum you could ever have for the most ideal eclipse, not this one, April 8th, but like the perfect longest lasting eclipse imaginable, totality in the middle of the path of totality could last as long as 7 minutes. So that's kind of the upper limit.
Ooh.
Where we are and this eclipse, we're going to be 1 minute and 50 seconds. But if you travel south from Hamilton towards Lake Erie, you could get up close to, and into part of the Niagara region, you could get up closer to 3 minutes rather than the 2 minutes that we'll have. So if you're right in the center of totality, you have a longer time where the sun is completely blocked.
Right. And so poor Priscilla, I have to let you know, can you see it from Toronto?
Well, you will have a really good partial solar eclipse, almost complete, but not a total solar eclipse. You will not be able to look with your naked eye safely at the sky. But if you come down to Hamilton or St. Catharines or Buffalo or Port Dover, you'll be able to see the total solar eclipse.
So for all those people in Toronto, that's a reason to come to Hamilton.
It's true. And in fact, I mean, I really do think that there's a chance that it will be quite busy on the roads. And there's even been some discussion about maybe adding extra GO trains that day to bring more people, because you don't have to go far. I mean, Burlington will be totality. Oakville, not quite. Mississauga, not. And so if you want to experience totality, you might want to come this way. And I can tell you, based on the 2017 eclipse that some of my colleagues went to see, what I heard was, when there's a total solar eclipse, a lot of people will drive to try to experience totality. So the traffic, lots of people will flood to a region, but they tend to come in over an extended period of time, maybe the night before, maybe the morning of, but over an extended period. And then as soon as it's over, everybody hits the highway at the same time. So if you are in the GTA and you're planning to come this way, my advice to you would be to make some nice dinner reservations and not rush to go home, because everyone's going to hop on the highway at the same time.
So speaking of that, if it gets dark, so if you're on the highways and you're I'm thinking like the QEW, especially if you're going from Hamilton to St. Catharines or to Niagara Falls, and it starts to get dark, like, are people going to get sort of anxious, and then, do accidents, like when you're talking to your colleagues who have experienced, like especially I guess Rob, when he went down further south in 2017, like do people kind of just stop? Does it become a bit hazardous?
Well, that's a good question. I mean, I hope that most people won't be on the highway. It's a brief period, and we hope we'll have the word out enough that everyone decides to make it an event and try to experience it. It will certainly feel eerie if you're driving along and suddenly out of nowhere it starts to get dark. I mean, it's going to be an eerie feeling. And actually, during the eclipse of 2017, we did not have a total solar eclipse here in southern Ontario, but we did have a partial solar eclipse. And so I was actually driving on the 407 during the best time to see it. And we pulled over and made a quick pinhole camera so at least we could see it, so we would experience it. Most people had no idea what was going on because it was only a partial eclipse. It was still bright out. So you wouldn't know unless you were in the know. But during a total eclipse, it gets much darker. And so it would feel pretty eerie. And hopefully most people will not be on the highway at that time.
Right. In 2017, when we had the partial eclipse, McMaster did, I think, like the sidewalk astronomy, the students who run the sidewalk astronomy had their big telescopes out. And so they had it safely, like, so you could see something. And I remember a few people had colanders. And so you could see in the colander, like in each of the holes, it was like the pinhole, and you could see it sort of half, right? It was just, it was pretty cool. I had brought my children at that point were like 12 and 9 or something. It was quite exciting, like, and the lineup to look at one of the telescopes that was properly filtered, was like, I don't know, 200 meters long.
Yeah, so it was actually my PhD student who was organized that. So the solar viewing telescopes with a safe solar filter that everyone could see was incredibly popular, and it would be nice if we had absolutely tons of them, so more people could experience it. But I would stay tuned for more announcements about things to come as we get closer to the date. So we luckily had somebody online who was telling us that the Royal Astronomical Society is selling solar viewing glasses. They will also be doing public events. McMaster astronomers will be doing public events. The Hamilton amateur astronomers, which is another group, will be doing organized events. So as we get closer, stay tuned to, and if you're in a different community, stay tuned to astronomy outreach events in your community, because there will be a lot going on. And in some places, there's probably will be telescopes set up so that people will be able to get a view. The other thing I should note too is that if we're really, really clouded out, and yes, it'll get a bit dark, but you don't get to see it, there's always going to be a live stream of this. So for example, NASA will be live streaming it, but so will other organizations. So from a place that has a good view, there will be a live stream available if you want to experience that.
So if you can't get it 3D, you can get it 2D.
Yeah, if you can't be there in the flesh, at least you can watch it on a screen.
So, sorry, I'm looking at some questions here. So Claire, thank you, Claire. She has given me clear skies here, so I'll put that in the resources.
Great.
Ron is asking, what will be the best direction to face on April 8th?
So the sun is going to be, it's 3 in the afternoon. So it's going to be high in the sky, a little bit towards the west. So because it's not so far afternoon, the sun's going to be nice and high. So you should be able to see it from almost anywhere. It's not like you're trying to catch an event that's right on the horizon where you need a great viewing angle. So as long as you don't have a huge apartment building directly to your west, then you should have no problem seeing it from almost anywhere. But in general, being somewhere that has nice open views of the sky, here in Hamilton, I would think like Bayfront Park would be fantastic, somewhere where you have good view of a big chunk of the sky, but it's going to be pretty high overhead, so nothing special.
Yeah, so but don't try to get in your car afterwards, right? So if you're going to go down to Bayfront, maybe bring a picnic or whatever.
Yeah,
because getting in and out of there.
Just don't expect to get anywhere really quickly afterwards. Yes. I mean, that's where we are here in Southern Ontario, there's a really high population density, and there's a whole lot of people who are just beyond the line of totality, who know I would be the same. I would want to be on this side of that line. So I just expect there's going to be a lot of people.
Oh, so Jennifer's asking, could you, it was my comment, my joke about astronomy for dummies, which it's not called. That's what I just affectionately call it because I'm not very math and science oriented. But it actually, Jennifer, wasn't continuing education. It is a second year astronomy course.
That's right.
Under physics and astronomy, 2B03.
Yeah, astronomy 2B03, the big questions, and it's a lot of astronomy, but also some of that general relativity I just talked about at the end, a little bit of quantum mechanics. What's different about this course compared to all the other courses in our curriculum in physics and astronomy and all the other stuff I teach is that it's taught at a conceptual level and people can take it from every background. So it's a second year astronomy class, but it's for students from every faculty on campus. So we have business students and philosophy students and engineers, everybody takes it.
Yeah, it was interesting being in the tutorials that I don't think physics and astronomy students take it. It's everyone else. And I remember you saying we only had to learn 2 equations. So if you don't like math like myself.
Yeah, 2 equations. You never had to plug in numbers. One of the 2 equations was E equals mc squared, which I think most people knew before they stepped foot in the classroom.
Yes.
Yeah.
So Ryder has a question about the sun bending the gravitational fields in space. Is there a point at which the sun does not affect a mass rotating around it?
Well, let's back up here. So the curvature that's caused by a mass, the bigger the mass, in fact, and the higher the density of the mass, so the more mass per unit volume, the more it's going to curve space-time. And the further away you get, the less and less curved it is. So objects in orbit around the sun are all moving in this curved space around the sun, but eventually you'll get out far enough where the gravitational influence of the sun will no longer be dominating and you'll be feeling the gravity from something else. So yes, there's a limit to the sphere of influence of every object. The curvature is strongest close to the object and it gets less the further you get away.
Thank you. Okay, so this is a really interesting question that Rick is asking. Would it be possible to get in a plane and fly along inside the shadow of totality? How fast does the shadow actually move?
Oh, that's such a good question. And if I were offline right now, I'd be playing with that website I pointed you to where you can plot along exactly where the totality is. So I don't want to answer this off the cuff without looking it up. So I don't think you can fly fast enough to move with the path, but I would want to confirm exactly how fast that is offline. Apologies, I can't do that on the fly.
That's okay. Okay, so, oh yes, so Donna was asking, can we see a recording of the eclipse perhaps on NASA website or what other website can we see it? And I think you did say NASA.
Yeah, I think there'll be a ton afterwards, but I know that in previous ones, NASA has certainly live streamed views of eclipses. So this eclipse was coined by some Americans as the Great American Eclipse of 2024. Of course, it's the Great North American Eclipse because it starts in Mexico and goes all the way to Newfoundland. So it's really a huge arc across a huge amount of North America. It's not just the American eclipse, but because it is also totalities going across the US, NASA and other American outlets will certainly have live streams for sure. And I suspect there will be Canadian equivalents.
So actually, can I ask you a question then? And I'll get to, wait, there's lots of questions here. So is the arc, it will always change, correct? Based on what you were talking about, like the orbit. So sometimes the arc could be longer, depending on the orbits of both the Earth and the moon.
Exactly. So you get these different tracks depending on exactly the geometry of that particular eclipse. And so these are the predicted paths for the upcoming eclipses over the next 15 years. So you can see they all have unique shapes and all has to do with the geometry of where's the sun, the moon, and the earth, and where are they in their orbits.
So Rick is also asking, if we have a telescope already, is it worth getting a solar filter for it?
I would think so. Yeah. And I would order that soon. Yeah.
Oh,
And also you can also get solar filters for some binoculars as well if you have binoculars. And if you don't manage to get a filter for your binocular, do not look through them, please. But you can direct the sunlight through them and project it. So the optics might get hot. Don't do it for too long, but you can project through binoculars as well.
so Priscilla's asking, and maybe you just want to reiterate, is it all right to just use sunglasses?
Definitely not. You need solar viewing glasses that are rated to safely filter sunlight to protect your eyes. Do not use sunglasses. And remember, take them off, your solar viewing glasses and your sunglasses, during that brief period of totality. You don't need them. And if you're taking images, if you have a telescope, maybe you have a camera with a filter. Also, you can't take a nice picture of totality if you have your solar filter on. Take it off during totality.
You know, it's interesting because I always thought that it was totality that you, for some reason, that you couldn't view. Well, I didn't think you could look up at any point, right? And to be safe, but now that's interesting. You have clearly said, no, totality is the safe time.
Yeah, I mean, it's so easy to damage your eyes by looking at the sun that historically, I mean, the conservative approach is just never, ever, ever, ever look at the sun. But the reality is that during totality, it is safe, but either side of totality is absolutely unsafe. And so I think the conservative advice and what we learned in school was just never look. And in fact, historically, which is sort of unfortunate, that when total solar eclipses have happened during daytime, school kids have often not been allowed to go out. Window shades have been pulled closed because everyone's so afraid of kids damaging their vision, and there hasn't been accessibility to have safe ways of viewing it, that a lot of school kids who were in paths of totality didn't get to experience total solar eclipses. So we're hoping that's not going to be the case for this upcoming one. So there's a lot of education going on and working with school boards along the path of totality, hoping that hopefully kids will get a chance to experience this. What's interesting is that totality is happening right at school let out time at in the afternoon. So that's a particular challenge as well.
Yeah, because you can't keep them inside then.
Yeah, but how do you make sure that it's safe and that nobody damages their eyes? By giving every single Hamiltonian a pair of solar viewing glasses.
That's what I was about to say. So public health is behind that. So Rick is asking a question. Will McMaster be organizing a trip to Australia to see the next solar eclipse, full solar eclipse?
Not so far, but I'll take a ticket if they are.
Yeah, me too. We'll do an event down there for our alumni living in Australia.
Great.
Oh, and so Joanne was asking, and maybe we can tie this in. So, you know, you sort of spoke about how there's more things to come with McMaster being involved. You know, we're really hoping to encourage people to come to Hamilton to look. So do you want to talk a little bit about what McMaster's doing? And Joanne's asking, you know, who is the name of the professor looking after the eclipse planning, which would be Rob.
So the main person, I'll just back up, apologies for flipping through the slides. The main faculty member so far who's been leading a lot of the efforts is Dr. Rob Cockcroft, who's pictured here. So I'll bring up this picture for you. So he's a teaching professor in astronomy in the Department of Physics and Astronomy. And he also he's the faculty member in charge of our planetarium on campus. So one of the things we're going to be doing for a lot of local outreach is just a ton of planetarium shows leading up to the eclipse, explaining some of the same stuff I was explaining to you today, but for audiences within the planetarium. But in addition to Rob, we're also in the process of hiring an event planner and manager. So that person is coming on board, I think, very soon. So this month sometime. And then we'll ramp up in being able to announce some of the other activities. So stay tuned. I suspect you'll hear a lot more in January and February about the local events. There'll be a lot of things leading up to the eclipse, as well as some events happening on the day of. And lots more to come, but the event planner is just being hired right now.
Excellent. Yeah, so we'll put them to work. So there's a few I know let me ask the final two questions, if that's okay with you, Laura.
Of course.
So another about safety, would welding glasses work?
That's a great question. So short answer is if you don't know exactly what your welding glasses are, the answer is no. If you know the level, then the highest level of welding glasses, which I think, and I'd have to look this up to confirm, is level 4, that those are safe. So the strongest welding glasses are safe for solar viewing, but most are not. And so I would follow Claire's link from the RASC to purchase a pair of solar viewing glasses potentially if you're unsure of what kind of welding glasses you have.
Better safe than sorry, I think is
Exactly.
the
Yeah.
motto we want to go with. Sorry, Peter asked something at the very beginning and I missed it, so I apologize, Peter. So it's going back to the lunar eclipse and the light refraction. So he would like to know, is any of the red color seen in a lunar eclipse due to differential refraction of the sun's light by Earth's atmosphere?
So it's really the thing that's dominating is really the scattering that I was talking about, which is called Rayleigh scattering. So the light from the sun comes in the entire rainbow, everything from purple to red, and the bluer the light is, the more it gets scattered. And so the only light that makes it through all of that amount of Earth's atmosphere, bounces off the moon and comes back to us, is the reddest part of the light from the sun. So it's really the fact that blue light is preferentially scattered by our atmosphere and only the red light survives and can bounce off the moon. That's why it looks red.
Oh, right, okay. Oh, and one final thing before, so this is a comment, not a question, but Dan is saying, in a June 1973 solar eclipse, the Concorde chased the path and spent 74 minutes in its shadow.
There you go. So you have to
shadow.
go at the speed of the Concorde, which unfortunately is no longer operational, but that makes sense to me because it moves really fast.
And it looked really eerie. When you showed that picture, it was kind of creepy. Well, I think I'm just looking to make sure we have, and I know we're a little over time. So thank you to everyone for your patience and for all your questions. Such great questions. Thank you, Laura, for taking the time to explain about, what sort of some of the scientific discoveries that have come out of eclipses and why they're so important to the scientific community, but why they're also just so enjoyable for the lay astronomer or person. Or Jennifer and myself who enjoy astronomy for dummies. So thank you, everyone. You will be getting a recording of this within the hour. And if you are looking for, I'll post in some of the information, what Claire had suggested about RASC. I'll put some of those resources in so that you can go and look for those and you can share those resources with people so that everyone will view the solar eclipse next April safely. And if you're in the Hamilton area, keep looking at the McMaster website. I'm sure once that individual who is hired, who is going to manage that, we will be posting information about what we're going to be doing, what McMaster and the city of Hamilton will be doing to facilitate a wonderful viewing of the eclipse. And we just all keep our fingers crossed that we will have nice weather on April 8th. Thank you, Laura, and thank you, everyone. Have a great evening. Take care.